Okay. Are we ready to go? Troy, you have a question to start with?
Yeah.
I haven't said anything confusing yet, have I?
No.
Okay.
Does he try and figure out how magnetism works?
Yeah, that's exactly it. At this point, you see, this morning we saw the experiment that he went through, his magnetic pendulum experiment, that indicated that to the extent that you can isolate magnetic poles, ignore the other pole, that they do obey an inverse square law. The magnetic force obeys an inverse square law just like gravity and electricity. But now notice nobody has said anything about how magnetism works. In the sense, remember we had a theory from Franklin about how electricity works. He had this whole electrical fluid and the way it interacted with ordinary matter. He had all that worked out to explain all the experiments. Well, nobody's said anything so far about magnetism. So Coulomb thinks, well, it'd be nice to have something for magnetism like the theory we have for electricity. And he gives it some thought, and what he comes up with is this. In parallel to what Franklin did, he says, well, there's a magnetic fluid too, okay, like there's an electric fluid. But what Coulomb suggests that this magnetic fluid is like, it's like a swarm of little tiny particles, okay, each one of which is a little magnet. Now, Coulomb figures, well, that explains why, for instance, you can have an iron bar, okay, that is not magnetized. And then you can put it next to magnets or rub magnets against it and magnetize it. Okay, well, what's Ben?
You magnetize it by charging it up?
Oh, you mean just giving it an electric charge?
Yeah.
No.
What do you mean by not having it not magnetized?
You can have a piece of iron that, that is not a magnet.
Yeah.
Okay, let's say you have a bar and it's not magnetic. But then you bring a magnet up to it, and that's what people did with like steel needles. If they wanted to magnetize them, they would rub magnets against them, and then they figured out how to do that in order to make it so one end of the needle would be a north pole and the other end would be a south pole. Now, according to Coulomb, what's happening in that case? Well, he says this inside the steel or the iron, there was already all of these little particles. Okay, I'm going to exaggerate the size of them, but they're in just random orientations, and some of them are pointing one way. It's like some of them will have a north pole on this end, some of them will have a north pole on this end. They're random orientations. Okay, and so half of them have on the average, are oriented so, say, their north ends are pointing north, but the other half are oriented so their north ends are pointing south. And so all these little magnets are just canceling each other out in the ordinary case. But when you put this bar next to other magnets, so there's a magnetic force on it, then all these little magnets tend to line up, okay, with the big magnet that you've put next to it. And so that's why, that explains how you can start with a piece of iron that isn't magnetized and get it magnetized. Daniel?
But wouldn't that mean they'd be all bunching up, and so all the ones that are bunching up would repel each other? Wouldn't
Oh.
be bunching up, and so all the north poles would be aligned, and they won't.
Well,
won't they
here's
repel each
what Coulomb figures happens. Let's say that you have all these things lined up. So I'm going to draw in. All these little elongated particles. And each one of them now is oriented the same way. Let's say, this is the north end, and this is the south end. Okay, for everybody in this row. But then this row, that's the north end. This is the south end. So,
That's the same as the first row. So.
yeah, right. They're all lined up this way. But notice that this way, see, this answers Daniel's question because he asked,
I'm asking, okay,
oh, you're at,
okay, the one below the first one.
yeah.
How is that north not repelling the north above it?
Oh, it would be, but you have to, it's also being held in this position by this one next to it, right? Because this is a north pole attracting this south pole. So you just have to figure there's some arrangement where they can line up and still be such that is a stable condition, and they'll stay in that position. And Coulomb didn't work out all the details, but notice that this also explains why when you cut a magnet in half, you get two magnets. Because if, let's say you cut it here, well, you're still going to have a bunch of north poles lined up along that edge. So, yeah, Troy.
But did he say that this magnetic fluid was only in like iron and lodestone and stuff?
Yeah,
Oh.
right. That's now again. I told you that there were things wrong with Franklin theory that I'll tell you about later. That the essence of Franklin's theory, as I gave it to you, is right, and that's why it explains so much. But there is something wrong with it. Well, there's something wrong with this theory too, but it's definitely on the right track. Nick.
Does his theory explain why it can attract some metals and not others?
Oh, yeah. Well, what he, I think what he assumes is that this magnetic fluid is confined to iron and maybe a few other materials like nickel or something. And so that's the only materials it can attract. Neve.
Zach explain how it can go through objects magnetism?
Oh, well, in a sense it does, because if you put, let's say, a piece of paper here, and then you have a magnet, and then you have another piece of iron, say, over here, well, it will, if this is the north end of this magnet, it will induce the magnetic particles in this magnet over here to line up so that this is south, and it will pull on those. Now, the reason the paper doesn't matter in the case of magnetism is because it doesn't have any magnetic fluid, so it basically doesn't respond at all to the magnetic force. Whereas the reason the paper will stop the electric force is because all objects on Franklin's theory have this electrical fluid. Okay, so what would happen if you took a positively charged, say, piece of glass, and then you were trying to attract, say, an object, some hanging metal foil over here, and you put a paper in between. Well, it would attract the negative charges of the paper to this side. Okay, and so that would shield the electric force from getting through the paper. So there is a difference here because most objects don't respond magnetically, don't have this magnetic fluid. They won't block the magnetic force. Troy.
What were these particles like supposedly microscopic or?
Yeah, he assumed they were really small. Now, the other thing his theory explained that Coulomb points out is, people had noticed that when you heat up a piece of iron, when you heat up a magnet, what happens? Yeah, it'll lose its magnetism if you heat it up enough.
Will it come back or will it always stay?
Well, once it's lost it, you would have to magnetize it again. It won't just automatically come back when it cools. Now, according to, on Coulomb's theory, how would you explain that? What's going on? When you put this to the flame to this thing and really heat it up, it loses its magnetism. Daniel?
The heat is killing the particles.
Killing them? Are they alive to begin with? Nick?
They're moving around too fast.
Yeah, what happens is that according to Coulomb, it's agitating these particles and disorienting them. Okay, so by heating them up, they won't stay in the right positions to give you a magnet. They'll get disoriented like this again. So that is, that was the basic idea, which is not a bad theory. It's a good start. Yeah.
If like iron doesn't become back into a magnet when it cools down, you said earlier that there are iron layers in the earth that are changed because of the earth poles keep switching.
Oh, right.
Then how do they become magnetized?
Oh, how is the iron in the earth magnetized? Because it's hot? Is that the question?
Like when it cools down.
That's a terrific question. At this time, people didn't know how hot the interior of the earth was. That wasn't discovered until later. But as soon as people did discover it, that became a major question that scientists asked was, well, if in order to destroy a magnet, all we have to do is, heat it up to, I don't know, a couple thousand degrees, or 1,000 degrees, or whatever it is. Well, if we know later they were going to discover that the interior of the Earth is hotter than that. I mean, it's hotter than the temperature that's required to destroy magnets. And yet, the Earth is a magnet. That's pretty strange, huh? Turns out there's another way to make a magnet, which we're going to learn about in this class. But that's a great question. Okay. So now, but notice what's going on here. I've told you that these theories are on the right track, but I'll give you a hint as to what's wrong with them. I mean, look what's happening. When people start out with this idea of ordinary matter just having mass, okay, and then Newton discovers that mass attracts other mass, and there's a force of gravity. Then they start investigating electricity. So what do they do when they come up with a theory of electricity? Well, they say, well, not only is there this ordinary matter that we started out with, but there's an electrical fluid in addition to ordinary matter. Then they study magnetism. And they say, well, not only is there ordinary matter and this electrical fluid, but there's a magnetic fluid that we're going to add. Okay, shortly after this, they started studying heat. Okay. Now, heat flows between bodies like electricity does. Okay, you can make heat conduct, down a long object and transfer it to another object and so on. So they started describing heat as a fluid. So matter is starting to get really complicated here, right? I mean, you've got ordinary matter, that just has ordinary mass. And then you've got electrical fluid, then you've got magnetic fluid, then maybe heat is a fluid. Well, eventually physicists would figure out how to come up with a theory of matter that includes, you know, gravitational attraction, electrical forces, magnetic forces, and explains heat, you know, just with one theory, rather than adding a separate fluid every time you have something to explain. And eventually we'll get to that. That is what's wrong with Coulomb's view, is that he explained it in terms of a separate magnetic fluid. It turns out you don't have to, but the rest of his idea is basically right. Okay. Now, we're done with really the first part of the history of electricity. Now, Coulomb has, you know, the forces that we started with, these attractive and repulsive forces of rubbed amber and rubbed glass. We now know the basic mathematical law that those forces obey, and we have, in essence, a right theory of what's going on. So this sort of wraps up the first part of the history of electricity. They're doing great experiments. They're using mathematics, you know, the way Newton did, and discovering basic laws. So this is a really pretty mature science at this stage. But there's something crucial that's missing from what we've said about electricity so far. Because the fact is, I mean, the kind of electricity that we're all most familiar with is not created by rubbing things. Right? Is there, what's missing from what I've said so far about electricity? Any ideas? Drew? Well, I haven't talked about the relationship between electricity and heat, but what gives rise, what are you thinking of? What gives rise to heat what is the connection between electricity and heat? Did you have anything specific in mind? Oh, okay. Neve?
Haven't talked about how electricity can be used.
Right, we haven't talked about how it can be used. And that one of the reasons is that the form of electricity that we actually use is different than this static electricity we've been talking about. Daniel, what were you going to say?
I was gonna say something about static electricity.
Yeah, but okay, but complete the thought. I haven't finished it.
What was the question?
What would you contrast with static electricity?
That it's done with pressure or contact or movement or something.
Well, I mean, if I'm going to say there is static electricity versus, Nick?
Well, we never really have, we have some things, but most of the time our electricity comes and goes instead of being kept.
Yeah, it's not sitting there. It's
Always moving.
It's always moving, continuously moving, which we call electric currents. I haven't talked about currents at all yet, right? I mean, the closest we've gotten to currents, really, is when Gray would charge up one object and then hook it through a 700-foot wet string to another object and then test that the other object got charged up, right? So there was a momentary current. And people actually tried to measure the speed. Remember I told you at one point that somebody strung a wire 2 miles long and tried to measure the time delay, but it was so fast that he couldn't really measure the time delay between when he hooked the wire to the second object and when the second object would charge up and move his electroscope. So only thing we've seen so far is momentary movements of electricity that take a split second and then they're over. But when we plug a wire into the wall here, we're just getting a continuous flow of electricity all the time. It's not a momentary flash. Troy.
If there's if you have an electroscope set up during a thunderstorm, and
Yeah.
Lightning comes down, would it ever move toward where the lightning went, or not?
Oh, no, it wouldn't. Nick?
Do we have a speed for how fast electricity moves now?
Oh, yeah. I'll get to that later. I mean, there's very fast is the answer. It actually if in the 2 mile long wire, the time interval between when you would detect electricity in the other end of the wire is it's almost it's not quite the speed of light, but it's approaching the speed of light. It's fast. Okay, now so I need to tell you how people discovered how to generate continuous movements of electricity, because that's going to be the absolutely crucial thing that leads to all of modern technology. Rubbing balloons on your head is great for class demonstrations, but it doesn't really do much for modern technology. So we need to generate continuous electric currents. And the guy who made the first discovery that led to this is an Italian who wasn't even a physicist. He was a professor of anatomy at the University of Bologna. Not Bologna. Let me see. It's Luigi Galvani. And so you can anatomy professor at University of Bologna. His dates are 1737 to 1798. Now, what is an anatomy professor doing monkeying around with electricity? Troy?
He could be studying anatomy and find electricity. Like he's studying.
Well, in effect, that's what he does, exactly. Galvani did a lot of dissections, and he worked a lot with frogs. So, studying the muscle structure and the nerves and so on. And but he was also interested in electricity. So he had one of these spinning electric generators in his lab, and he even had it on the table where he did his dissections on the frogs. And let me see, I'm going to call the rest of this lecture Dead Frogs Dancing. You'll find out. This was Galvani's great discovery: how to make dead frogs dance. And we're going to see. Well, very little in the case of frogs. In fact, Galvani, we'll see, made a significant dent in the frog population of Italy. But let me start out telling you the very first thing that Galvani noticed. One day he was dissecting one of his frogs, and his assistant was playing with the electric generator. And he had his frog on a metal plate, and the table itself must have been conducting. And Galvani had a scalpel that he had, stuck into the frog, and the frog was on this metal plate. And when his assistant drew a spark from the electric generator, the frog's muscles jumped. Now, basically what had happened was that the discharge from the electric generator that electricity had gone through the frog. And it made the frog's muscles contract and jump. Rachel?
The frog was dead, right?
Right. Right. Yeah, no, it's easy to see how something alive could contract its muscles, but it's more unusual among dead things. So Galvani figured he was onto something here. I mean, what he had noticed was a real connection between electricity and physiology, how the body works. Rachel?
So his assistant was just randomly playing with the electrical?
Right, they weren't actually trying to send an electrical discharge through the frog. They had done it accidentally the first time and noticed the frog jump. So then they started doing it on purpose, of course. And so the first thing that, let me just call this number one. The first thing that Galvani discovers is, let me see, an electrical discharge through a dead animal causes the muscles to contract. And he checked to see if, make sure that this didn't just work on frogs. He used chickens, sheep, and ox. Yeah, you need a big electrical current for an ox. But his assistant actually went on the road with this show, and he would set up public demonstrations where he had a big spinning electrical generator, and then would discharge it through, say, the back legs of an ox, and it would kick its legs, and people would actually get pretty distraught watching that. Selah.
They never tried that on people, did they?
Yes. Again, this is Galvani's assistant. He managed to arrange to get the body of an executed murderer, and like an hour after the execution. And then he shot electricity through the various limbs and made the guy raise his arms and kick his legs. Yes.
Isn't that leading up to the one thing that you go like that?
Is it?
Isn't this leading up to the one knee that the medicine? I don't know what it is.
Oh.
Charge you.
Oh, yeah. I mean, that's right. I mean, if your heart stops, they can force the heart muscles to contract using an electric shock. And doctors do that in emergencies now. Rachel?
How would
What would move if they put the electrical blanket?
Oh, in other words, how would they say if they wanted to move this arm? Yeah, well, okay, the electricity has to go through that arm, obviously. So they would have to, attach one contact here, say, and one contact in the hand. And then the electricity would go through the arm. So now you can imagine actually what this led to in terms of, does this remind you of anything that you've seen in the movies or literature? Yeah, absolutely. JJ got it. Frankenstein. Frankenstein was written just 20 years after this or so, and it was inspired by exactly these scientific discoveries. The fact that science could, with electricity, take a dead body and make it move. Okay. Now, that is not Galvani's most important discovery, but it set him on the path of investigating the relationship between electricity and bodies. Studying electricity through bodies. Well, his next idea, which I will call, let me see, Dead Frogs Dancing. I'm going to abbreviate that DFD. DFD on the balcony. Okay.
Were they gonna try and scare the neighbors?
So the next thing Galvani does is he has the idea, well, what if he were to take his frogs and hang them out on the balcony when there's a thunderstorm coming overhead? And maybe the atmospheric electricity would set his frogs moving.
Stick them on the roof and put a metal stick in
But now this turned out to be a very useful thing for Galvani to do, because let me draw exactly what Galvani did. Now, he had an iron grating on his balcony. So he's got these iron bars. Yeah, you can draw this. So let's say here's the vertical bars. Oh, floor's down here someplace. And then he's got horizontal bars. Okay, yeah, it's like a fence, an little iron fence. Now, he hangs his dead frogs on a hook. So this is iron, and this is brass. He has his dead frogs on brass hooks. And so here's I don't know quite how to draw a frog, but yeah, this is really an excellent frog. Okay. Okay, there's my frog. Now, that's right, I don't have arms, but it turns out the arms aren't too important in this case, so I'm going to leave them off. Well, artistic license here. Galvani actually cut the heads off, so the frog shouldn't have heads, but I drew the head just because it looks more like a frog. Now, okay, now. So, here's the situation. And Galvani did notice in this situation that when the frog's legs would touch the lower iron bar here, that he would see them twitch. Now, what surprised him the most was, he thought he would only see the frog twitch when there was a thunderstorm, because he was assuming at this point, when he first tried this idea, that somehow it was the atmospheric electricity of the thunderstorm that was, getting into the frog. Because remember, in his first experiment, he needed the electric generator and a discharge from his electric generator in order to make the frog move. So he thought, well, the electricity has to come from somewhere, so it has to come from the thunderstorm. Well, what really surprised him was, even on a clear day, this worked. Didn't need the thunderstorm at all. All he needed was his brass hook plugged into this dead frog and the feet touching the iron railing. Yeah, Rachel.
So what would happen if there was a thunderstorm? Would it
Oh.
just be the same?
Yeah, it would just be the same. It would not noticeably different. Drew.
Did you ever try putting him on a kite and flying it up in the air?
No, he didn't try that. But he did try other things that I'll tell you about in a minute. But this, as you can see, now this gets Galvani excited because this is even more, this is really a new discovery, more amazing than the first one. I mean, here you're taking an electric generator and sending the electric discharge through the frog. It's not that surprising that that would make the frog twitch. But here, there's no electric generator. There doesn't even have to be any thunderstorm in the area. Clear day, and all you need are these frogs on their brass hooks with their feet touching the iron railing, and you and you make them dance. Yeah. So now, where is this electricity coming from? Well, Galvani starts to think about these dead frogs as like little Leyden jars, almost like they've got this electricity in them, and somehow all you have to do is hook a conductor into one end of them and a conductor at the other end, and hook them together, and you can get this electricity to flow through the frog, to move through the frog. And that's, of course, he already knows that the muscles contract when there's electricity moving through the frog, right? So when he sees the muscles contract in this situation, he figures there's electricity moving through the frog. Well, seemingly all you have to do is hook them up to conductors, and this happens. So frogs are like little Leyden jars. Cows are bigger Leyden jars. Animal bodies are Leyden jars. At least that's Galvani's first thought. Now it turns out he's wrong about that. But Rachel.
Did he only try it with frogs?
Oh, yeah. No, the cows didn't work nearly as well on the balcony. They took up too much room.
What if it got a big balcony?
Now, what was that?
What if they got like a really big balcony?
Okay. Ben.
Never mind.
Okay. Now, next step. We got a few minutes left, but Galvani decides to try this in the lab, not just out on the balcony. And so his third experiment is he takes in his lab, he takes a silver platter And then he takes his frog, okay, feet on the platter, and again, the hook, let me see, what does he have here? And he's still using brass at this point. Brass, by the way, is a combination of copper and zinc, two different metals. Zinc, it's a kind of metal. And he connects his brass hook here to the silver platter, some connecting wire. And what do you think happens then?
It keeps shaking. Like, doesn't.
Yeah, the frog's leg muscles start contracting. He starts kicking. He starts dancing on the silver platter. Yeah. And this works even better than the iron railing did out on his balcony. He finds that silver works even better than iron. The frog will just keep going. Now, let me see. Oh, well, I'll leave you with one. Now, Galvani doesn't know what makes this work, okay? So he tries it for a whole bunch of things. He tries replacing the silver platter with some glass platter, okay? Finds out that doesn't work at all, okay? You need conductors, okay? Then, I'll get to your questions in a second, but I want to tell you the one astounding thing he discovers, okay? And he really should have realized this was even more important than he thought it was. But if you take, for example, replace the silver platter with a brass platter, so both the hook up here and the platter are both made of the same metal, brass, frog won't kick. Now, isn't that amazing? Selah, you had your hand up first, I think.
I was wondering, did the frog have to be recently dead?
Yeah, he couldn't be too old.
How old is too old?
Well, I'm actually not too sure. You have to be a biologist to know, when exactly the muscle decay is, and rigor mortis sets in so much so that he won't kick no matter what. But they kick for a day, I think, or at least a few hours. Drew.
Did you ever try like having like a silver, but silver on like one side, like where one foot is touching the silver, and then having on the other side have copper or something like that, or brass?
Yeah, that would work. What he finds is you have to have two different metals. If you use the same metal, no matter what the metal is, if you use the same metal, it won't work.
No, I mean
But
platter.
the platter itself, you have 1/2 brass and 1/2 silver. If this were brass and this were silver, then, yeah, right, a one-footed dance, huh? Yeah. Rachel.
If you have like a iron platter and an iron hook thing,
Right.
it wouldn't do.
Won't do a thing. It takes two to tango. Two different metals. Okay. On that note, I'll talk more about this next week.